Welcome to SSR Pharma Media, your trusted source for pharma knowledge. PIC MCQ series, your exam power boost, Pharmaceutical Inorganic Chemistry. In that, today we are going to discuss about volumetric analysis. Prepare, practice, succeed. Volumetric analysis. So, we are going to cover fundamentals of volumetric analysis, acid-base titration, non-aqueous titration, precipitation titration, complexometric titration, redox titration. So today in this video we are going to cover only fundamentals of volumetric analysis. The fundamentals of volumetric analysis. So today we are going to discuss about titration, what is titrations, and importance of primary and secondary standards used in the titrations, and methods of expressing concentrations. It's used for the preparation of solutions. In volumetric analysis, so titration, what is titration? Define titration. So titration is an analytical method in which a solution of known concentration, that means titrant, is added to a solution of unknown concentration, is called analyte, that means titrate. So until the reaction is complete, allowing determination of analyte concentration. So volumetric analysis. So titrant is a type of known solution of known concentration. So it must taken in the burette. And analyte, that means titrant. So another name is called it is a titrant. It is taken in the burette. Analyte is another name is titrate. It is taken in the conical flask. It is a type of solution of the unknown concentrations. So taken in the conical flask. It is a substance to be analyzed. It is also called as titrate. And the end point is the changes, produce color changes. So we'll see the concept of titrations. So titration is the types of quantitative methods of determining concentration of an unknown solution by reacting it with the solution of known concentration. The process involves the gradual addition of titrant to analyte until the reaction is complete. And examples, titrant is a known concentrated solution taken in the burette. Analyte, it is also called as titrate. It is a type of unknown concentration and it is taken in the conical flask. And equivalent points. What is equivalence point? So equivalence points theoretically, it is a type of theoretical point where chemically equivalent amount of titrant and analyte have reacted completely. So it is called equivalence point. It's also called as end point. So that means it is coming after this point, produce end point. So example, determined by stoichiometric balance of reaction. And end point, so after the equivalence point, practical point. It is called practical point. Theoretical point means the reactions takes place between the titrant and analyte can't be seen. So only the reactions will happen. So after the equivalence point, it is also called end point. It is also called practical point. So observed during the titration whereon indicator changes color. So indicator produce the changes color. So approximate of equivalence point. So example, it should coincide closely with equivalence point for accuracy. Endpoint detection. How to detect endpoint means, so in the types of different type of volumetric analysis will detect in the different color changes. For example, acid-base titration, pH indicators are used. So in order to detect the endpoint, indicators are used. In acid-base, we will use pH indicator like phenolphthalein, methyl orange. In non-aqueous titration, Also, it's a pH indicators. We'll use crystal violet. And precipitation titrations, we'll use adsorption indicator. It's called fluorescein. And complexometric titration, it is a type of metal ion indicators. So, it is example is areochrome black T. And in redox titration, so redox indicators or self indicators, so it is nothing but titrant of KMnO4. And in examples, instrumental methods, potentiometric method, conductometric method and spectroscopic method. And in these instrumental methods, we won't use any type of indicators. So, what does mean indicators? So, indicators means the substance that show visible changes of color or turbidity or potential near the equivalence point to indicate endpoint. Next, we will move into the questions. So, till now we have discussed about the fundamentals of volumetric analysis. Now, we will see the questions, important questions. Titration is the best defined as. So, answer is option A. A method to determine solubility of a substance. So, process of adding, answer is option B. Answer is option B. A process of adding a solution of known concentration to a solution of unknown concentration until the reaction reaches completion. So, this is the correct answer. So, titration is an analytical technique in which a standard solution of titrant is added to an unknown solution of analyte until the reaction is complete, usually detected by an indicator or instrument. In a titration, the solution of known concentration is called. So, the answer is option C, titrant. So, known concentration is also called as titrant. It is always taken in the burette. In a titration, the term analyte refers to, so the answer is option B, the solution of unknown concentration placed in the conical flask. So, it is a type of unknown solution placed in the conical flask. The main purpose of titration is to determine, so the answer is option B, concentration of an unknown solution. So, in volumetric titration measures the volume of titrant required to react completely with the analyte to calculate its concentration accurately. So, which of the following is not essential for a successful titration? So, the question is not essential. So, the answer is option D, high boiling solvents. So, remaining three are very important in order to successful titration of the titrations, but it is not required. High boiling solvent. The equivalence point in a titration is defined as, so the answer is option B, the point where the reaction between titrant and analyte is stoichiometrically complete. The difference between the equivalence point and the end point is mainly due to presence of indicator behavior. So, the end point depends on the indicator color change, which may not occur exactly at the equivalence point. The smaller the difference, the more accurate the titrations. So, that means when we are doing the titration, slight color changes leads accurate titration reading. During an acid-base titration, the end point is defined as, so the answer is option B, the practical point where the indicator shows a visible color change. It's called end point. So, the end point is the observable color change shown by the indicator during titration. It is an approximation of the equivalence point. For accuracy, The endpoint should be as close as possible to the equivalence point. Which of the following best describes the functions of an indicator in titration? So the answer is option B, to show a visible color change near the equivalence point to signal the endpoint. So indicators are the substance that exhibit a visible change, mean colors, turbidity or potential near the equivalence point, helping the analyte detect the endpoint of the titration. They do not affect reaction speed or pH. Which property of an indicator is most essential for accurate titration results? So the answer is option B. It must undergo a visible change close to the equivalence point. So now we'll see the standard solutions. Standard solutions with accurately known concentration used in titration. So it is called standard solutions. So whatever the solutions we are using in the titration, so that solutions are called as standard solution. And in standard solution there are two types are there, primary standard solution, then secondary standard solution. So what is primary standard solution? Means it's prepared by dissolving accurately weighed pure substance. It must be stable, non-hygroscopic and high molecular weight and readily soluble. So these nature of the substance are called as primary standards. So example, sodium carbonate, potassium hydrogen thalate, oxalic acid, silver nitrate and potassium dichromate. So these are all the examples of primary standard. And what is mean by secondary standard solution? So secondary standard solution it is a type of concentration determined by standardizing against primary standard. So often it's unstable or affected by air and light. So it is unstable and it's affected by light and air. So such type of substance are called as secondary standard solution. So example, sodium chloride, potassium chloride, sodium hydroxide, potassium permanganate, sodium thiosulfate. So these are all the examples of secondary standard solution. So primary standard solution provides a reference point for the accurate chemical measurement. Secondary standards allow routine analytical work since they are easier to prepare and handle. In volumetric analysis, so you see the examples of primary standard and it is used for this titration. For example, sodium bicarbonate is a type of secondary primary standard substance and it's prepared as a solution, primary standard solution. It is used for standardizing the acids of hydrochloride. So potassium hydrogen thalate is primary standard. It is used for the standardization of acid base like sodium hydroxide. And silver nitrate is a primary standard. It is used for the standardization of halides like sodium chloride. So like that, you take this screenshot and you read this example. It's very, very important for the exam point of view. And these are also examples. So suppose this hydrochloric acid is a secondary standard and it's standardized against sodium bicarbonate and it is used in the acid base titration. Same like that, sodium hydroxide, it is a secondary standard substance. It is used to standardize against potassium hydrogen thalate is a primary standard. So it in the acid base titration. So like that, for all substance given as an example. So this also you take a screenshot. So which type of secondary primary standard and secondary standards used in titrations. So you read it thoroughly. It is very important for the exam point of view. We'll move into the questions. Which of the following is not true about a primary standard? So the answer is option C. It is hygroscopic in nature. So primary standard is not a hygroscopic in nature. Such type of chemical substance only can be as a primary standard. A suitable primary standard should possess which of the following characteristics? So the answer is option B. High equivalent weight and chemical stability. The property of primary standard that ensures accurate weighing is option C. High equivalent weight. So reduce errors in mass measurement and improving precision in titration. Which of the following is a commonly used primary standard for acidimetric? So the answer is option B. Sodium carbonate. So sodium carbonate is a primary standard used in the acidimetric methods of titration. So because in acidimetric methods we will use HCl or sulfuric acid as a titrant. So we will take a known analyte of sodium carbonate in the type of acidimetric titration as the primary standard. Potassium hydrogen phthalate is used as a primary standard to standardize. So the answer is option B. Sodium hydroxide. So potassium hydrogen phthalate is used for the accurate preparation of sodium hydroxide solution in acid-base titration. Which of the following substances can act as a primary standard in redox titration? So the answer is option B. Potassium dichromate. So potassium dichromate is used as a standardized ferrous solution in redox titrations. Oxalic acid is used as a primary standard because it, option C is answer, has a definite compositions and high purity. Identify the incorrect pair. So you identify the incorrect pair. So the answer is option D. Sodium hydroxide is a primary standard for acid. It is wrong because sodium bicarbonate is used as a primary standard for acid, not a sodium hydroxide. This is the correct answer. So option D is the correct answer. So it is incorrect pair. Which characteristic applies to secondary standard? So option C. It must be standardized frequently. Secondary standards are typically, so answer option B, unstable or hygroscopic reagents. So substances like sodium hydroxide and potassium permanganates are reactive or unstable, hence not suitable as a primary standard. Sodium hydroxide is standardized using. So sodium hydroxide is standardized using. So the answer is option B, potassium hydrogen phthalate. Iodine solution is standardized using. So option A, arsenic trioxide. Potassium permanganate is standardized by option C, oxalic acids or sodium oxalate. Sodium thiosulfate solution is standardized using option B, potassium dichromate. Which of the following pair is correctly matched? Correctly matched. So the answer is option C, potassium chromate and primary standard. So sodium carbonate is a primary standard, hydrochloric acid is secondary standard, KMnO4 is a secondary standard. It is not a primary standard. So potassium dichromate is a primary standard. This is the correct answer. Is C is the correct answer. So match the following. The answer is option A. So option A, sodium bicarbonate is a standardization of acids, and potassium hydrogen phthalate is the standardization of base, and silver nitrate is the standardization of halides, and oxalic acid is used as a standardization of oxalic acid is used for the standardization of base, and potassium dichromate is used for the standardization of oxidation and reduction titrations, and arsenic trioxide is used in the redox titration. So here, so correct answer is option A. Next, match the following. In this correct answer, option A. So sodium hydroxide is the option. Sodium hydroxide is option 1. Match the following. Sulfuric acid is 1. Match the following. And potassium permanganate is 2. Redox titration. Iodine solution is iodometric titration, and sodium thiosulfate is the redox titration. So the answer is option A. Is the correct answer. So next we will discuss about methods of expressing concentration. Methods of expressing concentrations. So these are all the parameters, concentrations of solutions: molarity, molality, formality, normality, and formality. So these are all the methods of expressing concentrations. So and molarity is a definition: moles of solute per liter. Molality, moles of solute per kg of solvent. Normality, equivalence of solute per liter of solution. Formality, formula weight per liter of solution. So this you take in the screenshot and you read it carefully. So definitions. So these are definitions of each terms. Concentrations. Molarity, it's a symbols capital M, and it if you dissolve 1 mole of sodium chloride in enough water to make 1 liter. So this solutions leads to 1 molar sodium chloride. And molality, so 1 mole of sodium chloride in 1 kilogram of water. So that leads molality, it's a small m. Normality is a capital N. So here, if you dissolve 1 mole of sulfuric acid in 1 liter, it leads to normal of solution. That means it leads normality solution. Here we will use equivalent weight. So 2n, because 1 mole is equal to 2 equivalent. And formality, so dissolve 1 formula weight of sodium chloride in water to make 1 liter of the solution. So these are definitions of the normality, molarity, molality, and formality. And we will see the formula of these methods of expressing concentrations. So molarity means weight of the substance divided by molecular weight into volume. So capital M is indicating molarity. Molarity is equal to weight of the substance divided by molecular weight into volume. And normality means number of equivalent weight of the substance divided by equivalent weight into volume. So you in these two formula there is the difference. Here molecular weight, here equivalent weight. So difference between molarity and normality is a difference are there. Molarity means we will take the molecular weight of the substance, and in normality we will take equivalent weight of the substance. And what is equivalent weight? So equivalent weight means weight of the substance that react with or it's equivalent to 1 mole of hydrogen or 1 mole of hydroxide or 8 gram of oxygen it leaves 1 gram of hydrogen ion. So that means equivalent weight means it's a combining capacity of number of hydrogen ions, n number of hydrogen ions or hydroxide ions. So numbers that leads equivalent weight. The relationship between molarity and normality. So relationship between molarity and normality, this is the relationship. So n is equal to n into m, where n is equal to number of equivalent per mole. This molecular weight of the substance, equivalent weight of the substance. So this is the relationship, is the variations in this formula. So we'll move into the question. Molarity is defined as, so the answer is option C, moles of solute per liter of solution. Normality represents, so the answer is option B, gram equivalent of solute per liter of solution. Which concentration unit ignores dissociation in solution? So option C, formality. Which of the following remains constant with changing temperature? So option B, molality only. So which is incorrectly matched? So the answer is option C. Normality means formula weight per liter. It's a wrong, incorrect. So the correct answer is for this question option C. 1 mole of sodium chloride dissolved in 1 kg of water represents. So 1 kg of water means, so of course it's a molarity. So option A is the answer. 1 mole of sodium chloride in 1 kg of water. So it is molar, it's a small m. Molarity is not molality. So molality means it's moles, 1 mole of dissolved in 1 kg of water. It's a capital M means molarity. So 1 mole of solute dissolved in 1 liter of the solution. So here they asked kg. So molarity is the correct answer. 1 molarity, capital M means molarity. H2SO4 solution behaves as 2N because, so option C, it gives 2 equivalents of hydrogen ions. So normality depends on equivalence. So that means hydrogen sulfate, it gives 2 number of hydrogen. So that means it's equivalent valency of H2SO4. So 58.5 gram of sodium chloride dissolved to make 1 liter of solution. So it is called, so option B, it is the 1 liter, it is option A is the answer, 1 molarity. So 1 formality solution. So option B is the correct answer. So option B is the correct answer. So sodium chloride molecular weight 28 and sodium is 28, chloride 35.5, it leads 58.5 gram. So 1 gram weight of the sodium chloride and dissolved in 1 liter of solution, it's called 1 formal solution. What is the molarity of solution containing 9.8 gram of H2SO4 in 1 liter of solution? So the answer is option A, 0.1 m. So molarity formula, weight of the substance divided by molecular weight into volume, number of liters of volume. The equivalent weight of H2SO4 in acid-base reaction is, so option A, 49. The equivalent weight of sodium hydroxide is 40. Because in sodium hydroxide, so only one replaceable OH is there. So it leaves 40 divided by 1 is equal to 40. The relationship between molarity and normality is expressed as, so option B, capital N is equal to small n into m. Normality is equal to number of replacing hydrogen atom into molarity. So what is the normality of 0.1 m H2SO4 solution? So the answer is option C, 0.2 n. So here replaceable hydrogen atom is 2. So 2 into 0.1 is it leads 0.2 n. If the normality of solution is 0.5 n, what it is molarity? So option B, 0.5 m. So you substitute in this formula, n is equal to n into m. So here the normality, we want to find out the molarity. So m is equal to n divided by capital N divided by small n. So capital N divided by small n. Capital N they have given as a 0.5 normality. So capital M is given divided by and normal 0.1. Capital N divided by 1, it leads 0.5. A solution is prepared by dissolving 5 gram of sodium hydroxide in 500 ml of water. What it is molarity? So option C is the correct answer. Substitute in this formula, weight divided by molecular weight into volume. Volume you should write in a liter. And you will get the 500 ml of what you have 5 gram of sodium hydroxide should dissolve in 500 ml water. So that means it's a volume you have to put in the liter. Liter means 0.5 liter. 500 ml is equal to 0.5 liter. So substitute in this formula, you will get 0.25 molarity. What is the molarity of solution containing 4.9 gram of H2SO4 in 250 ml of solution? So the answer is option B, 0.2 m. So all these questions you practice by your own in order to find out the answer. So molarity, this is the formula. While substituting, you must care about this volume in liter. So 250 ml they have given. So you have to substitute 0.25 liter. So 250 ml is equal to 0.25 liter. So 25 ml of 0.1 n HCl neutralizes 20 ml of sodium hydroxide. Find the normality of NaOH. So the answer is option C, 0.125. So here formula V1N1 is equal to V2N2. So V1 already they have given N1 already they given 0.1 n. V1 also 25 ml and N2 don't know and V2 they have given 20 ml. So if you are substituting in this formula, you will get the answer 0.125 normality. So and you must know the difference between normality, molarity. So molarity means how many grams of sodium hydroxide are required to prepare 25 ml of 0.1 n molar solution. But here grams required. Here in this normality, how many grams of sodium hydroxide is required to prepare 250 ml of 0.1 n normal solution. So 0.1 m 0.1 n solution you are going to prepare. So you must see the difference between molarity solution and normality solution. So here already they have given molecular weight for sodium hydroxide. So sodium hydroxide molecular weight is 40 and in both solution they ask one for molarity solution and one normality solution. We are going to prepare. How many grams of sodium hydroxides are required to prepare 250 ml of 0.1 m solution? 0.1 m solution. So we require 1 gram of sodium hydroxide is required to prepare 0.1 m solution. And how many gram of sodium hydroxides are required to prepare 250 ml of 0.1 n solution? So the answer is option B, 1.0. So substitute in this formula, equivalent weight molecular weight divided by number of replacement hydrogen atom. So only for the normality we have to use this formula, equivalent weight formula. Molecular weight of sodium hydroxide is 40 and number of equivalent replacement hydrogen OH group is 1. So 40 divided by 1 is equal to 40. Then weight of the substance, normality into equivalent weight. So normality 0.1 we want to prepare and equivalent weight is 40 and how much volume we require? 0.25 liter. So it gives 1 gram. And in molarity normality already were discussed. So for the preparation of hydrochloric acid molarity we require to prepare 250 ml of 0.1 solution, and for hydrochloric acid are required to prepare 250 ml of 0.1 solution. So how much we require? How many grams of hydrochloric acid are required to prepare 250 ml of 0.1 solution? So option C, 0.91 gram. How many grams of hydrochloric acids are required to prepare 250 ml of 0.1 solution? So the option C is the answer. So molarity normality, you read it by using this slide. And how many grams of sulfuric acids are required to prepare? If you see in this slide, sodium hydroxide 250 ml to preparation require 1 gram. So in molarity solution, normality also is required 1 gram. But at the same time, hydrochloric acid also required 1.91 gram for prepare 0.1 molar solution, and this also 0.1 normal solution. But there is the difference between preparation of H2SO4. So H2SO4 replaceable number of hydrogen atoms are present. So it changed the quantity. 2.45 grams are required to prepare 0.1 m molarity solution, and normality solutions require 1.225 gram. So for this question answer is option C. How many grams of sulfuric acids are required to prepare 250 ml of 0.1 solution? So here option C, B is the answer. So you take the screenshot and read this slide. And parts per million is defined as option B, and ppm of sodium chloride in water means, so answer is option B. A solution containing 1 mg of fluorides in 2 liters of water, its concentration in ppm is option B. Parts per million represent option C. 5 microgram of impurity per liter of water is equal to option C. So water sample containing 20 ppm of lead, this means, so option B is the answer. Match the following. The answer is option A is the answer. You read it. Primary standard is the best defined as, tell in the comment box. So thank you. All of you join in our WhatsApp community. You will get hands-out material and number of test series. Thank you. Like, subscribe and share.